Hi everyone, welcome to the first video presentation. My name is Hao Bo and I will present the first part. In the first section, I will briefly introduce the overview of this course. Just like what is the nature of matter for physics, computer science has its own fundamental questions. What is an algorithm? What can and what cannot be computed? The purpose of this class is to study of computing machines, their fundamental capabilities and their limitations, and introduce us to some ideas and models which are powerful and beautiful to answer these questions. So we have the motivations to learn this course. Let me use a figure to illustrate the fundamental question clearly. Let's say we use the circle to represent all problems, and we have the computability theory to classify them into two categories, the solvable problems and the unsolvable problems. The classification problem is answered by this class in principle. Then, looking into the solvable problems, we can develop algorithms to solve them in practice, and the complexity is researched by the complexity theory. And then there is another question. What is an algorithm? The algorithm is a finite set of instructions to complete some tasks. So we use the algorithm to solve solvable problems, and of course we cannot find an algorithm for those unsolvable problems. All questions lead to the below tasks. Devise a model of computation that is as universal as possible, then use the model to determine problems as solvable or unsolvable. From this class, we will learn some restricted models like finite automata, regular grammars, regular expressions, and we will also learn context-free grammar and push-down automata and a universal model Turing machine. Before the course, let's review some basic knowledge. We say B is a subset of A if every element in B is an element in A. And we say two sets are equal if A is a subset of B and B is a subset of A at the same time. Note that it is very useful for proving the claim of two sets is equal. The sets have operations like intersection, union, and difference, and the power of a set is the set of all possible subsets. And the notion of the partition operation is also shown in the figure. Moving on, and then we have the relations and functions of sets. Know that bijection is important for us to prove some theorem like countability later. We also have the equivalence relation, reflexivity, symmetric, and transitive. We have a variety of symbols like numbers and letters. Then the set of infinite symbols is an alphabet. We call the finite sequence of symbols the word. And words have the operations such as concatenation, reversal, and power, which means m copies. We call a set of words over an alphabet language. Correspondingly, the language also has some operations like concatenation, reversal, power, clean star, and plus. The clean star and plus operations may be new to us. Why language is important in computation? The reason is that the language and computation models we will learn later are intrinsically related. Do you still remember the solvable question? Given a positive integer, is it even? With the definition of language, we can convert the problem into an equivalent language recognition problem. So besides we know it is solvable, we know how to solve it. On the other hand, there is a challenge when we consider infinite languages, which is exactly the central issue of the computation. So there is an important result. No matter how powerful the model we use for representing languages, only countably many languages can be represented, so long as the representations themselves are finite. To understand this claim, we need to know the knowledge of the countable and uncountable. We say that a set is countable when it is finite or it is equinumerous with n, the set of natural numbers. Otherwise, it is uncountable. Here we introduce two important proof techniques. The pigeonhole principle, it can only be used in finite sets. The diagonalization principle, it is very useful to prove a set is uncountable. Finally, we have the major result that in any representation system, there are always some languages that do not have finite representations, so unsolvable problems exist. Knowing that unsolvable problem exists, in the next section we are going to learn the finite automata, a language recognition model, as well as the simplest model to solve some solvable problems. First, let me introduce some concepts briefly. Regular expressions are defined as the finite representations of language over sigma 1. Regular expressions are used to represent the patterns of words. For example, a word in the form of AB, AB, AB can be represented as AB clean star. If we use alpha to denote a regular expression, a language can be specified as L alpha, which is a regular language. An important property is that regular expressions are closed under concatenation, union, clean star, reverse, and also intersection and complementation, which can be proved after learning DFA. As we mentioned before, a finite automata is the simplest machine with only a finite number of states. Consider a vending machine. It will decide whether to sell the good or not. According to the input, here is the money it receives. In the beginning, the machine will be in the initial state, and the state will change according to the money you put in. An instance is that it will sell you a good if you put in $2. After reading all inputs, if the state is in the final state set, your input is accepted by this machine, which means you will buy it successfully. Otherwise, you will not be accepted, which means you cannot buy it. To be more mathematical, a DFA is a quintuple like this. In terms of NFA, there are mainly two differences between NFA and the DFA. Firstly, some states may have more than one outgoing edge with the same symbol, and it will try all possible in this case. Secondly, the edge may be labeled with E, which means NFA allows direct translation between states. Due to these two changes, we can easily design an NFA. However, we can prove that every NFA can be converted into a corresponding DFA, which means NFA doesn't provide additional computation power.
Okay, so next we are going to introduce some of the important properties. Firstly, there is an equivalence relation between regular language and deterministic and non-deterministic finite automata. Here, the equivalence means that a language space which can be represented by regular language and finite automata is actually the same. The proof is based on the construction method. You can make corresponding regular expression from arbitrary finite automata, and also you can make corresponding finite automata from arbitrary regular expression. In the lecture, we will learn this specific construction technique. Also, we will learn the closure property of regular language. The regular language is closed under concatenation, union, clean star, and reversal, as well as intersection and complementation. Lastly, we will introduce pumping theory for regular language. Pumping theory is a property that all of regular language must satisfy. Therefore, this property can be used to prove a language is not a regular language. This proof will be based on contradiction. First, assume L is regular language, which means it must satisfy the pumping theory. Then you are going to show that it does not satisfy the pumping theory. This fact leads to a contradiction of the first assumption. Hence, it is proven that L is not a regular language. Here, please be noted that by using pumping theory, you can only prove that a language is not regular. You cannot prove a language is indeed regular language. All right, let's move on to the next section. In this section, we are going to learn context-free language. This is a new class of language, and it also has its generator and recognizer like regular language. So what is context-free language? Context-free language is a larger class of language than regular language. For example, the language which is not a regular language, such as n times of A concatenated by n times of B, is context-free language. The relationship of these languages is like this Venn diagram. The set of all regular language is included in the set of context-free language. However, please be noted that even the context-free language has still limitation. For example, simple language such as I times of A followed by I times of B and C are not context-free. In later lecture, we will cover the even larger language class which can include this language. Like regular language, context-free language can be expressed by generator and recognizer. The generator is called context-free grammar, and the recognizer is called push-down automata. The relationship is similar to the one of regular language. Okay, so let's dive into the important aspect of context-free language. In the lecture, the following 4 topics will be discussed. First, let's discuss its generator. Let's start with the example rather than a formal definition. Context-free grammar produces words by applying rules one by one from the starting symbol. Suppose we want to generate words belonging to this language. Then context-free grammar is like follows. Context-free grammar has components which are the start symbol, alphabet, terminals, non-terminals, and rules. Here, alphabet is a set of all letters used in this grammar, and the terminals are the alphabet which can be used in generated words. Non-terminals are the alphabets that cannot be used in generated words. And most importantly, we have rules. Those rules will be applied one by one. Let's look at the right diagram. It shows how the words are generated by applying rules. We first start with S. Consider the first branch. If rule 1 applies, then it generates an empty word. Otherwise, rule 2 applies and generates ASP. It still has non-terminals letter S, so apply a rule. Next rule. If I apply rule 1, then it generates the word AP. If you don't apply rule 1, you can use rule 2. This process can continue to generate all of the possible words. This is a procedure of how context-free grammar generates words. Lastly, you might be wondering why it is called context-free. This is because context-free grammar restricts the rules to have only non-terminals on the left-hand side, which means those rules are not affected by the context of terminals around the non-terminals. And next, another important thing about context-free language is you can always construct context-free grammar from finite automata. In the class, we will learn this construction method and be able to make a context-free grammar from any finite automata. Also, at the same time, this is a proof of the fact that context-free language is a larger class of language than regular language. Okay, so let's move on to the recognizer. The recognizer for context-free language is called push-down automata. Push-down automata are similar to finite automata, but there's one crucial difference. Additionally, push-down automata has a component called stack. This component makes automata more flexible and makes possible representative language space even bigger. So let's see how push-down automata work. What is the difference with finite automata? The crucial difference is the stack component, as I mentioned. This is an example of transaction relation from push-down automata. It consists of the state of automata, the location of the head of the tape, and stack-related elements called pop and push. Okay, so how can this relation be used? First, suppose we are on the left side situation. Here, please be noted we have 2 arrows pointing tape and stack component. Here, the top of the stack is B. Therefore, you can pop B from the stack component because this is the top of the stack. Therefore, this rule can be applied. Then we change the state to S2 and push new element A to the stack. This is how push-down automata works. Okay, so this is a recognizer, but it's not clear that it recognizes the context-free language correctly. However, it can be proved that it is true. The proof is based on construction technique too. You can always construct corresponding context-free grammar from an arbitrary push-down automata and vice versa. This way of proof is similar to the proof between regular language and finite automata. In the lecture, we will also learn the concrete procedure of the construction technique. In addition, we also learn about the closure property of context-free language. It can be shown that context-free language is closed under union, concatenation, and clean stir. However, not closed under intersection and complementation. This is an important difference from regular language which satisfies all of those 5 properties. Lastly, we are going to introduce pumping theory for context-free language. This property can be used to prove a language is not context-free. We learned the pumping theory for regular language, and the usage is very similar to the one in regular language. Next, in the last section, we will recap what we have learned in this video. In the video, firstly, we learned the purpose of the lecture. The crucial question we want to answer is what algorithm is. We also learned the problem space of unsolvable and solvable. Next, we recap the basic mathematics such as set theory and introduce the concept of language and word. Based on this foundation, we introduce the concept of finite automata and context-free language. Here, we briefly explain the corresponding recognizers, generators, and essential properties. This is an overview of the first part of this course. Thank you for listening.